In this video, I will be giving a brief review of Stat 155 and introducing the machine learning process. This graphic gives a high-level overview of the concepts you learned in Stat 155 and how they are connected. In that class, we focused on linear regression models. You learned how to interpret model coefficients, to make inferences from the sample the model was built on to the larger population, and to predict the response for a new observation. You also learned a couple ways to measure how well the model fit, like R-squared, adjusted R-squared, and sigma hat squared. Some of you may have learned about model assumptions and variable transformation. If not, don't worry, that will be one of the first things we discuss in this course. Most of you also were introduced to logistic regression, which is a way to model a binary response variable. Let's take a bit of time to review some notation from linear regression. We will build on this notation in this course. In the regression setting, we have a quantitative response variable, y. The response variable is also called the target, outcome, dependent variable, and variable of interest. Our goal is to model the trend in y using a function of the p explanatory variables. Explanatory variables are also called predictors, features, and independent variables. Linear models, or linear regression, make the special assumption that the function f of x is a linear combination of the explanatory variables, as shown in equation 2. Each individual observation can be written as in the third equation. Then, the estimated model, also called fitted line, model formula, model, line of best fit, and least squares line, is shown in the fourth equation. The beta hat j's are the values of beta j that minimize the sum of the squared residuals. This is shown in the fifth equation. Fitted values, or yi hats, are found by plugging in the values of the ith observation's predictor variables into the model. The residual is the difference between the actual value, yi, and the fitted value, yi hat. These data show the engine displacement versus the miles per gallon, MPG, for 2018 vehicles originally obtained from the EPA and further cleaned and made publicly available by Julia Silge. We can see from the graph and the model output that there is a negative, somewhat linear, moderate relationship. The blue line shows the fitted line. The purple vertical line highlights engine displacement values of 3 cubic inches. The purple horizontal line reflects the fitted value, yi hat, for an observation with a displacement of 3. The yellow vertical line highlights engine displacement values of 4 cubic inches. The yellow horizontal line reflects the fitted value, yi hat, for an observation with a displacement of 4. The distance between the purple and yellow lines is about negative 3.13, which reflects the estimated slope. On average, cars with a displacement that is 1 cubic inch larger will get 3.13 miles per gallon less. The intercept, 32.9, is interpreted as the average miles per gallon for a car with a displacement of 0 cubic inches. The red line segments represent residuals, the distance between the actual MPG and the fitted MPG, and are highlighted for just a handful of observations. The model R-squared tells us that about 0.55 or 55% of the variation in MPG is explained by engine displacement. So there's still quite a bit of unexplained variation. The sigma hat means that, on average, predicted MPGs will be off of their actual MPGs by about 3.75 miles per gallon. In order to better understand where linear regression fits into the machine learning process, let's look at our course flow diagram. If you rewind to the beginning of the video, you will notice that this is an expansion of what was shown in the first graphic. That is because linear regression is a type of machine learning. In your 155 class, you likely focused on interpretation of the model, with a small amount of time dedicated to how you might use it for prediction. In this class, we will focus more on how to use the model for prediction, and we will be very interested in finding models that have the best predictive value. That being said, we still think it's nice when we can understand the model, so we won't completely drop the interpretation piece. Next, let's examine a bit closer what happens inside the build, train, evaluate loop. This is where we see a big difference from what we are used to in Stat 155. Think of fitting one linear regression model as one of the analyze eval pairs. Those are the blue and green boxes. In this class, in order to better evaluate the performance of our models, we will divide up the data, fit models on a portion of the data, and evaluate how well it performs on the portion that wasn't used to fit the model. We will do this on different samples of data, and we also might try different types of models or algorithms. This will help us tune the parameters of whichever algorithm we are using. We also hold out a special portion of the data that we refer to as the test data. We save this portion until the very end when we want to evaluate the best candidate models to make a final decision about which one we will use. I have simplified this for now, but the details will come as we work through the course. Now that we have reviewed some basics from Stat 155 and have an overview of where we are headed, we are ready to jump into the first detailed topic, linear model assumptions. We start here for a few reasons. One, it allows us to build on linear models, which you are already familiar with. Two, we can learn some new R packages and functions while we are still discussing this familiar model. And three, it provides motivation for other machine learning algorithms because we see where linear models can fail.